Oh, hello. Today's lesson is simplifying Boolean statements with logic laws. So we've already seen how to simplify Boolean statements using truth tables. We're also going to need to simplify them using logic laws. Now, to do this, we're going to need a list of logic laws, but there is one handy. I've put it up on the screen over there, but there's also, that same list is in your information booklet and your course notes. So please be referring to that throughout the video as we go. In this video, I'm going to go through that list and we're going to talk about each one. Some of them won't take very long, some of them might be a little bit more complicated. And in the second half of the video, I'm going to go through a couple of examples of how you might simplify a Boolean expression using those logic laws. So the main skill here that we're going to be using a lot when we're doing this is pattern recognition. You're going to need to look at some sort of statement that's got variables in there like A's and B's and X's and Y's, and try and recognize what pattern they might fit to this list of logic laws. It will fit some pattern, and if it does fit a pattern, then we can use that law to simplify it or rearrange it. There's a lot of parallels with mathematics and algebra, and I'll use some of those where appropriate, but I'm cautious of using too many because sometimes the analogies break down. I'll explain that when they get there. Anyway, let's just jump into it. Let's have a look at these laws. It's important to note that some of these laws are so simple that they're obvious, but we still want to state them anyway so that when you're using them, you've got a way of referring to which law you're using. The first of these that is incredibly simple are the commutative laws. This tells us that A and B is the same as B and A. That's pretty obvious. It makes sense that it doesn't matter which order they go in. We're used to this in maths. You know that 3 plus 4 is the same as 4 plus 3. And so those things are commutative. Now, maths, we have to deal with non-commutative things. You should know that 3 minus 4 is not the same as 4 minus 3. So the subtraction operation is not commutative. In computer science and in Boolean logic, there are non-commutative operations as well, but we're not going to be looking at them at this level in this course. And so the main operations, the operators that we're looking at, and or, are commutative. The order doesn't matter. That's what law 1 and 2 tell us. Next up, we've got the associative laws. This is also so simple it might be obvious, but if we're doing AND with a whole bunch of different inputs, then we sort of have to do two at a time. We pair them up, but it doesn't matter which order we pair them up with. I can again use a maths example. We know that 3 plus 4 plus 5, I could add the 3 and the 4 together and get 7. 7 plus 5 gives me a total of 12. Or I could add the 4 and the 5 together first and get 9. 3 plus 9 is also equal to 12. And so it doesn't matter which order we do that 3 plus 4 plus 5 in. AND works exactly the same way. OR works exactly the same way. It only gets complicated if we've got ands and ors mixed together, but that's a different pattern. It doesn't fit this pattern. So the associative law just tells us with and, we can sort of do things in any, pair them up in any order, or we can pair them up in any order as well. Law 6 is pretty simple. I won't spend long on this. The law of negation states that not A is the same as A. That makes sense. The not operator just flips our zeros and ones, and so obviously if we're flipping our zeros and ones twice, then when we flip them the second time they flip back to how they were originally. And so if we start with a variable like A and then we not it and we not it again, we're going to end up with A. Now's a good time to point out that all of these things could be demonstrated with a truth table fairly easily. I'm not going to be doing any truth table work here, but if you're interested, it wouldn't be difficult. The first few are pretty simple. Some of the later ones are a bit harder, but still really interesting. If you've got a couple of minutes to demonstrate, do a truth table for them, convince yourself that it's true. If you need to actually see it, it will definitely help your understanding of both truth tables and of logic laws to build a truth table of this sort of stuff. Let's move on. This distribution law also has a mathematical analogy. If we've got something outside of the brackets, in this case A or outside of brackets, then we can distribute that A or into the variables that are inside the bracket. So here originally I've got a B and a C inside of brackets that can distribute to the A or B and A or C, each of which is in its own brackets. The distributive law works for ORs going into an AND bracket, but it also works for an AND going into an OR bracket. And so it just lets us take that A and put it into the brackets. Now's a good time to point out that we might have to go both directions on this. And so when you're doing that pattern recognition, you might want to be able to recognize, and let me get rid of some of these scribbles, you might want to recognize that something looks like this, and life will be better if we make it look like that because it'll let us see some sort of pattern. But also maybe life looks like this and we want to put it back like that, and we want to simplify it so that it recognizes some sort of pattern. That shouldn't be difficult. A good analogy is sort of algebra. We know that if we're doing something like 7 lots of x plus 3, you can expand the bracket and get 7x plus 21. That is a skill expanding that you're going to need to do in algebra and in maths all the time. But also going the other way, that factorizing is also a skill you're going to need to do. Similar here. Now the next one is De Morgan's law. This is super critically important that you understand. De Morgan's law is fundamental to so much Boolean logic, but it's also kind of tricky because it breaks down our maths analogy. This doesn't work the way expanding brackets in maths does. So it's time to now put away those analogies. Let's just think about what's actually going on here. We've got a not outside the bracket. If we expand that not into the bracket, then sure enough we get a not A and we get a not B. But what's happened in between? Before it was an or, now we've got an and. And so if we are expanding, putting that not into the bracket, then we have to make it the not A, the not B, but we also have to flip that symbol from an or to an and. Or in the other case, we have to flip it from an and to an or. And so we've got to be really careful of this. You've got to be aware of it. You can't just willy-nilly start expanding brackets and put the not where you think it should go for because you've done some algebra before. But it's not that hard. You've got this sheet in front of you all the time as a reminder, and anytime you're going to be doing any of this work, you should be having that page open on the information booklet. So it should be nice and simple. Those are some of the harder ones to understand. We're going to get into some simpler stuff now. The next simple one is the idempotent law. And the idempotent law just tells us that if we're doing an AND operator where both inputs are the same, then the output is just going to be whatever that input was. The AND operator doesn't do anything there. The second input is redundant. And so we just get out one of the inputs that we put in. And it doesn't matter if we're doing the AND operator or the OR operator there. Now, this is a really typical thing that I could say, if you want to do a truth table, do it. It'll make it obvious. You'll see what's going on with a truth table. You don't have to. Might help you understand it though. All right, now we're moving on to the second half of the table, and we're introducing a new variable now, well, sort of a new variable. You'll notice that this one, now we've got two new things there. One's T, stands for true, and a capital F, which stands for false. If you're visualizing these in a truth table, then the column for a capital T is a whole column full of ones. It's always true all the time. And the column for false is all zeros. It's always false, always zero, all the time. You don't have to visualize with it with truth tables, but it might help you. Now, the law of the excluded middle, what that tells us is that if we've got a variable and we do an OR operation with the opposite of that variable, as in A or not A, then it's always going to be true. One of those, when I say those, I mean A, and I also mean not A, one of those two things must be true at any given moment. And so if we do an OR operator between them, we're always going to get true. If we do an AND operator between them, then it's always going to be false. They're never true at the same time. So always one of them will be true, never will both of them be true. And so that means that this law of contradiction tells us that it's always going to be false if we're doing an AND operator. Now again, that's common sense, it's logical, it's obvious, but it is handy to have it written down explicitly so we can refer to it if we need to say that we are getting rid of a variable or simplifying something for a reason. Then we've got 6 laws called the laws of constants. These are pretty simple and obvious. Not true is always going to be false. Not false is always going to be true. Here, if we do an AND operator with a true input, then the true input sort of becomes redundant because we're comparing where this thing is true and this thing is true. But if this thing is always true, then this is the only one that matters. So we can sort of forget about that and just look at this one. That's how I like to think about it. And so A and true is always going to be A. Similarly, if we've got two inputs, this one could be true or could not, and this one here is always false, then when we do an AND operator, they're never going to both be true because this one's always false. And so the answer here is always going to be false. It doesn't matter what this one is, we're going to get false as an answer. So we can simplify something like that. Similarly, if we've got A or true, well, this one's always true, this one can change, but that means our answer is always going to be true because we're looking for either of them being up, true. And similarly, so that was law 25, and similarly, law 26 tells us that if it's A or false, and so this one could change, but this one is always false, then we only care about this one. If an OR operator is where I care about either one of them being true, and so if A is true, then that's what we care about, and if A is false, that's what we care about, and so we can simplify that to just be our A input. So those ones are all nice and simple. Again, if you want a truth table, go for it. It makes it really clear. And it's a good exercise for you to help your understanding. Now, the next one gets a little bit tricky. There's a lot going on with this next one. And it sort of might look familiar. We've got this A or situation into a bracket, which we've already seen. Let me get rid of some of my scribble over here because I want to demonstrate some things to you now. So I'll just quickly get rid of that scribble. All right. And so here we've got an A or situation, which we've already seen before. We've seen an A or. So law 27 and law 7 sort of look similar. The difference is that this third variable was C, whereas here, if our third variable is not something new, but is instead the opposite, well, if we expanded it using law 7, this C wouldn't be C, it would instead be not A. And that means... Sorry, I'll just keep my capitalization consistent. That would be instead be not A. That means we've got this A or not A situation, and we can use this A or not A situation to recognize that that whole thing is true. And if that whole thing is true, then now we've got this AND true situation, and so we can recognize that this thing over here, this law 23, is already AND true. And so that just becomes what the input is, which means I can get rid of all that, and we get left with A or B. And sure enough, what's our answer over here? A or B, because law 27 really is a combination of using law 7 and then law 14 and then law 23. And so if we do all those, we don't need law 27, but the fact that it's there allows us to save some time. So there are some laws that are derived from other laws. I'm not going to go into that theory too much. Law 28 is obviously the equivalent, but with our ands and ors swapped. Finally, we've got our absorption laws. Let's have a look at these last two. Again, we've got a similar situation. Let me rub out a couple of things here so I can draw more fun mess. Again, we've got a situation where I've got an A and, which is similar to this A and, but now what's in the brackets is not the opposite of A. I've got a duplicate of A in there. Now, that makes life kind of interesting, and strangely enough, it makes the other variable redundant. Let me give you an example of that. If we're talking about A or B, we need one of them to be true, but we also need A to be true. And so if A is true, if we need A to be true, and we also need A or B to be true, then if A is not true and B is, we're still false anyway. So we only actually care about A in this case. It sort of gets, the B sort of gets absorbed by the complexity of requiring the A to be true. Similarly, if those roles are flipped with our or and our and, we get the same result. A or A and B means that the B becomes redundant. We don't need A and B to be true if it's ORed with an A statement. That I'm probably lost you there. There's a lot going on, but really you don't have to understand it. And if you do want any more, I'll say it again, you can draw up a truth table. You can plot those things in and you see what they look like. All right, we're ready to move on. So Those are all the laws. You don't have to know them all in detail. You don't have to know them as much detail as I've explained them now. You just have to be able to recognize the patterns. All right, so let's have a look at an example where we're going to use that skill. Remember, it's all about pattern recognition. I am going to look at this particular question. This asks us to simplify this algebraic expression, A and B, or A and not B. First of all, I can look for things that seem familiar. I've got an A and in brackets and another A and in brackets. And if I have a look at my index law list over there, I can certainly see that here in law 8, I have an A and in brackets and an A and in brackets. Now, in this case, it's just coincidence the letters are both A, are all A, but in this example, if it was P and with P and, then I could say, oh, well, I've got the same variable with the same operator inside both brackets. That will let me pull it out. In this case, the difference is only capitalization, but that's something minor. We're not going to worry about that. So here, this logic law tells me A and means that I can pull the A and out of the brackets, and what I have left are those two. That's what I can do instead. So here, I am now going to pull the A out of the A and out of the brackets. That leaves me with what was left in there, a B, or what was left there, not B. Now, it's really important when we're doing this skill that we state what law we've used. That most questions in an exam will ask, tell you to state what law you used, and so it should be obvious then that this was law 8 that got us there. So I am going to put some square brackets around that and say law 8 is what got me there. All right. I haven't finished though. We should be able to recognize that I've got something there that I can simplify, that is B or not B. And looking at my list of logic laws, I can clearly see that B or not B is going to be something like this. Now, here's a good example of where I'm dealing with B's. The logic law list over there is dealing with A's, but the point is that it's the pattern that matches. It's a variable or not. Sorry, a variable or not that same variable. So the A is what's important there, that they're the same. Doesn't matter that it's A, it just matters that they're the same. And then here, again, since they're the same, we can do it, even though now we're dealing with B's and not A's. So that thing there is now equivalent. I'm going to use a new symbol. Actually, I should have used it before. We tend to use this symbol called equivalent. It's not quite the same as equals. I'm not going to go into the differences here. If you can basically use it anywhere you would use equals in maths, but with Boolean logic, we prefer equivalent to. And so that then is the same as A and true. I know that B or not B is true, and that's law 14 that tells me that. So sure enough, I'm going to write here, I used law 14 to get there. And now this and true thing I've seen before. Let's go back our pattern recognition. Whereabouts does something and true occur? It occurs right there. So I can use law 23 to get rid of that and true and just take the input variable. In this particular case, that is just saying that is equivalent to A, and I used law 23, get there. I can't simplify any further. When we get down to a single variable, that's it. So I'm finished. That's the answer to that question. I have simplified this expression. Let's have a look at another example. This one's slightly different because it's not asking us to simplify, it's asking us to prove that. It's slightly different. What it basically means is here we have a Boolean expression, and it is asking us to show that that is the same as that Boolean expression. Basically, we're doing the same thing as simplifying, but we know where our target is. We're starting with this thing on the left-hand side. We're trying to get that thing on the right-hand side. You can borrow some maths notation from here. If you've done any proofs in maths, I can very easily say left-hand side is equivalent to, and now just focus on the left-hand side, and eventually I'll get it down to the right-hand side. It doesn't really matter. We're not too fussed about the notation here, as long as you're being very clear about what law you're using at any time. So what law am I using here? Well, this one's a little bit more complex, but what I notice is I've got a pattern of A and B and A and B and so that sort of matches the same thing that we had back in law 8, where I've got a pattern with an and that is consistent across brackets. And thanks to my associative law, I know that I can treat that pair as a single thing. So what that means is that I can use the same law, this law this law 8, I'm using this same law here that has an A and an A and to pull that out, only what I'm pulling out in this case is the A and B. So I am going to pull out of the brackets A and B and then put into the brackets what I have left over, which is that C, or and not C can go there. And that's, again, law 8 that got me there. So now my pattern recognition tells me I've got a C or not C there. That matches this law of the excluded middle again, where I've got something or not something. So law 14 tells me I can turn that into true. I'm going to write that, A and B and true. And that was law 14 that got me there. And I know that an and true I can just get rid of thanks to law 23 again. And so in this particular case, I can say A and B, and that was law 23 that got me there. And what you'll notice is what we were aiming for was A and B. That means that I have found A and B, I have hit the right-hand side, and so I have proved what I needed to prove. Now, it's unfortunate those two examples turned out to be pretty similar. I didn't plan that, but it's not a big deal. Your job now is to have a go at some of your own. There are plenty on page 14 of the notes. So there's 10 questions there that I hope you can work through doing something similar to this. Can you just simplify them? And those questions also suggest that you should use a truth table to verify your answer. And so if I use this example 1 as an example, if I was going to solve this with a truth table, then I've got my A column and my B column with my input 0, 0, 0, 1, 1, 0, 1, 1. That's fairly standard for a truth table. I'll have a bunch of other columns here like A and B, and then a column that is probably not B, and then a column that is A and not B, so I'm getting each of those. And then I've got my final one, which is this statement here into there, A and B or A and not B, with brackets appropriate because we're not worrying about order of operations here. And if I know that these two things, I've used logic laws here, this whole step here is to use logic laws to show that this thing is the same as A. And so to do that with a truth table, I should end up with this column here being the same as this column there. I know I've done it right if those two columns match. So that's how you do it with a truth table. The questions for understanding on page 14 do ask you to use both methods and verify you get the same answer. So have a go at that now. Good luck. If you've got any questions, you can ask me anytime, anywhere, especially in the comments below if you want. I'm always happy to help. Thank you very much.